Welcome back, folks. So we have been discussing about graphs a lot. We have discussed about different types of graphs, how to represent them. We have also talked about DFS and BFS and their traversals. So today we are going to talk about one of the problems in graphs, that is the alien dictionary. So the problem goes like we have a list of words which are lexicographically ordered, and now we have to find out what exactly is the order of letters
of the characters in that language, right? Like in English, it is A, B, C, D, E, right? E, F, G, H, I, J, K, L, M, N, O, P. In here, W comes before E comes before R comes before T, and T comes before. So, and again, these are sorted, or we can say alphabetically or lexicographically arranged. Now, what does that mean? Now, let's talk a bit about this. What does it mean? We have words W, R, T. We have W, R, F, W, R, F. Then we have E, R, E, R. Then we have E, T, F, E, T, F. Then we have R, F, T, T. R, F, F, T. So what does it actually mean? So if I compare these two words, I can say that since it is alphabetically arranged, obviously W and R would come together, like in a dictionary, but T is coming before F. So T is coming before F. Interesting. Now, I'm pretty sure that W is coming before E. Yes, W is coming before E. All right. Now, what? W is coming before E. Other than that, F, we cannot check anything else in this particular case. Let's talk about these two. So E is E. R is coming before T. Okay. So R is coming before T. And E is coming before R. So let's do one thing. Let's bring R here, and R is coming before T, and T is coming before R. T is coming before F. That is already established. Interesting. Now, what we can see is that W obviously comes first, and then it's E, then it's R, then it's T, then it's F. So the obvious sort here is W, E, R, T, F, right? It's that easy. Now, not exactly. So it might not be in this way every time, right? Not all your characters might just be such linear expressions of graphs, right? And just like a linked list, it might not be. So it could be something like, say, this. W connects with R, then R connects to F, right? So what we do is we keep a degree, right? So what is the degree in a graph? The degree in a graph is the number of incoming edges. So an incoming edge for W is, let's say, just for the sake of simplicity, let's say it points to T as well. We get such an example where we can make sure that W is before T. Right. So the degree of T is 1 and 2. All right. The degree of R is 1 and 2. The degree of E is 1. So what we do here is we first remove W. We first print it here, and we remove it. So 1 degree is reduced from T, R, and E. So now E is 0, R is 1, and T is also 1. Okay. Now we take the next zeroth degree character, which is E. All right. So we take it out of our graph. Right. So since we have taken it out, let me just this is R, this is T. Right now R is 0 because nothing is pointing to R, there are no incoming graphs to R, and T remains 1. Right now we pick the next zeroth character, zeroth degree character, which is R. Now we print R here. Right now the degree of T is 0. Sorry, the degree of F was 2 here, now it's 1. Since R is no more connected to it. Now we print T, and then we print F. Because after removing T, F would be the 0th degree character. And then at last we remove F as well. So our graph is now empty. And if you notice, following that particular, even making it more dense, we are able to get the same output. So how are we able to get this output? If you notice, we used an algorithm called topological sort. In topological sort, we essentially do the same thing, right? If you remember it from your n-ary trees or binary trees, you may call it a level order, right? Or a level order is also a topological sort. And for graphs, what we do is we find the least number of inbound edges, and we say that it is the degree of that edge, right? So let's start. So when we would be creating our order, what we would do is we would need to have a degree which will keep a track of degrees of every character, right? Like here, what we did here was, if you notice, right, we were keeping track of our degrees. Right? I'm going back. You can notice that we have been keeping track of our degrees. Let's not go that back. All right, we're keeping track of our degrees. So let's have a character map. Let's have a C map, right? And we will have our characters and their degrees. Right? We'll take the same example which we used here, and we will walk through the code one by one, right? And I will try to explain you this as we go through the code. So the next thing is take a graph. Now, what we have taken a graph is, if you notice that graph, it seems a bit different, and we haven't covered it. It seems it is a map. Why isn't it a list or an array? And in a map, we have a set y. So if you consider this, it is basically an adjacency list, right? Because in adjacency list, we have an array, which is basically a map. And then inside a map, we have a set, which is a linked list. So rather than using a linked list, we are using a set y. I will come to that as well, because we would need to reference those vertices a lot, right? And rather than using linked list, using set and a hash set makes a lot of sense. So first of all, what we do is we build our graph, right? The first step which we did here as well was we built our graph file, checking these things. Now, what did we do while building that graph? So if you notice, first of all, what I did was I made a note of all the characters, right? All the characters. I made a note of all the characters, and so let's make a note of all the characters. And create a character map as well, just initialize it. So we have WERTF. We have W, we have R, we have T, we have F, and we have E. And the degrees are 0 because we don't know what their degrees will be, so we just initialize them to 0. Right? All of them. Right? Now we have another hash set of characters where we store our characters. The sequence doesn't matter because in unordered sets or hash sets, there is no sequence at all. We do not keep a track of the sequences. Now we have our character set. What we do here is rather than we create a copy of our character set so that we do not. So it's basically a coding practice. Whatever input we are getting, we do not mutate it, but rather than we create a new set. And we create a graph. Now, how do we create a graph? Now, if you notice, what we did in the previous step, we were checking 2 words at a time. Right? We are checking 2 words at a time. We do the same thing in the code as well. We start with our index, word index, right? We take the length, just one less because we need to take the next index as well. So just so we do not face any overflow issues. And we increment it. Now we get the current word and we get the next word. Now with the current word and next word, if you noticed, what I did was I checked, okay, W is equal to W, R is equal to R, but hey, T is not equal to F. So we can get some relation here. So iterating through all the characters, right? If my character at this particular index is not equal to my next word's character at that particular index, there's something interesting which I can do. And what is that interesting part? What I can do is, from the characters, I will remove that. I will remove that particular character. In this particular case, I will remove what? I'll remove T. Right? Why am I removing it? Well, we get to know it at the end while we are putting all the characters in the graph. So whatever isn't used, whatever isn't referenced, we just put all those characters in our graphs, and those characters do not have any vertices at all. Right? So let's move ahead. Now, what we are saying here is, if the graph does not contain any character yet, then add an empty set to it. All right. So what is our graph? We have created a graph. So a graph is, again, a character and a set. Right? So right now, I do not have any character. We have not initialized our graph at all. So what I'll do is, I know that the current character, which I'm referencing is T, right? And what does it have? It has F inside it as its edge, as its adjacent vertex. That's all what we are doing here. So we initialize with an empty hash set, and then we add it, and then we compute our degree. So if you notice, we are keeping our degrees here, vector map or degrees, right? We're keeping our degree here. Now the degree of F increases. See, F is the next character, and we are increasing its degree. So now F becomes 1. That's cool. Makes sense. Now we go ahead and we get to the next word. We get to these two words, and here we see that W and E are different. One more thing I just want to clarify here is that we're taking the minimum length of current word in the next words, because just so we do not overflow our indexes, right? Do not go out of bound of our indexes. So let's see. Yeah. So again, we move to the next word and we go character by character, and W and E are different. So we remove W now from our character set. We have removed W from our character set, and we are sure that W has to be added to our graph, and the next character has to be added as its adjacent vertex. So we do W, we do, and the adjacent vertex to my W is E, right? Adjacent vertex to W is E. All right, and I increase the degree here. It's coming out pretty nice. Now we go, then we check the next character, R and R, they're equal, then we can't go further because it's just two characters, right? Now we check these two, ER and ETF. E are same, R and T. We go to R and T. Now for R and T, we remove R. We add R to our graph. The vertex to the graph is T, because R is pointing to T, and we increase the degree of T by 1. Cool. Now we go to the next set. This is the next one, ER. Obviously, we remove E from our set, right? And we put it here, and let's just say we put it here, and it's pointing to R, right? And we increase the degree of R by 1. That works. Now let's come here. So T and F, same thing we do with T and F, and the other. It's actually T. Else it would not make sense. It has to be T. All right. So T comes after F. So we have already covered that, I guess. Yeah. So now what we have here is that, if you notice, we have W, right? Oops. Let's change our color, right? We have W as cardinality 0. All right, and whatever we have left is F. So I mean, just if you just go back to the code, F is left, and F is basically a leaf of our graph, the end of our graph, which doesn't have any more vertices pointing out of it in the outwards direction. So we just mark it null and we return the graph. Now we basically do a topological solve. How are we doing it? The first thing which we do here is we get our we get all the vertices which have 0 index, which have 0 degree, and we add them to our queue, right? And once we add them to our queue, what we do here is we take a string builder just to note down all our result, and then we pull from our 0 degree, from our queue, right? We get our vertex, we append that to our result. Now we get the set of neighbors, right? So if the neighbors is not null, let's say if there are no neighbors, we just remove that graph, right? Like we did while we are doing it, we're removing it, right? So the same thing we do, we remove our graph, right? And then inside our, if we find a list of neighbors, what we do is we count the degree. We reduce the count like we did here while we were doing it. We were reducing count of our neighbors as and when we were removing our 0 degree vertex, right? We are reducing count of all our neighbors, right? And if the count is 0, we are again adding it to our cube, which is a 0 degree cube, right? And if it's not 0, then what we do is we update its degree, like we did it here, right? We were updating its degrees, and if they were 0, we were just popping them out. In theory, we will be adding them to Q and popping them out, right? And at the end, once this entire process is done, what we do is we remove that vertex from the graph itself, right? So removal from sets is much easier. Okay, so that's the alien dictionary thing.
All right, folks, that's all for today. So I hope you like the series. Uh, just let me know if you would like me to cover any topics from system design or data structures and algorithms. Just drop a comment there and I'll sure come back to you. Thank you.